History of life on Earth. The Earth is over 4.6 billion years ago. It is thought that the universe is still expanding from the once large, humongous explosion that started over 16 billion years ago, where basically a small atom-like particle of mass that had the entire mass of the universe within it exploded and became the universe as we know it today. The Big Bang Theory, which is the most supported theory about how the Earth began to form, states that this explosion led to all the mass of planets and meteors, galaxies of our universe. Life on Earth, on the other hand, didn't start till much, much later. If you were to look at the time that the Earth has been in existence, which is around 4.6 billion years, and you were to start at 12 o'clock noon, you would have to go around the clock back to 12, let's say you start at 12 a.m. in the morning. The day begins, you go around, you go to lunchtime, and you come around again. And humans don't come down to Earth until the very last second of the clock striking that 24th hour. Dinosaurs are appearing on Earth around 11:30. And if you look at the Cambrian explosion, which is a time period at which organisms diversified, you're looking at like 10 o'clock. And if you look at the first organisms, you're really looking at around 3 billion years ago, 3.5 billion years ago. That's 3,500 million years ago. Photosynthesis begins around, first life is about 3.8 billion years ago, or 3,800 million years ago. So you just imagine that humans are occupying this time space of 2 million years out of 4,600 million years. Out of 4,600 million years, humans are only on Earth for 2 million of them. So just think about in relation to what we're going to be talking about and organisms on Earth, humans are not as big of a part of the ecosystem of the Earth as you would expect. Even though humans have a huge biomass on Earth today, it's not nearly as close as the biomass of most organisms like plants and bacteria. History started 4.6 billion years ago with the mass of all this kind of cloud particles of gas that kind of coalesced together to form the Earth. And the Earth was formed about 180 million years after the formation of the solar system, which was way after the Big Bang. The oldest measured rocks on Earth are about 4.3 billion years ago, and they're called zircon crystals. And these, you can find out how these crystals are formed by looking at the link over here. But these crystals basically form as the Earth was undergoing intense heat and pressure changes as a result of having just coalesced. And what's happening is the tectonic plates, the lithosphere, which is the part of the Earth that holds all the land masses, and all the land that the oceans settle on has not even formed yet. There is a lava type ocean by which it's just a bunch of hot material, very intense heat and chemical reactions with lots of electrical charges and pulses of the Earth. So it's a very hostile environment 4.6 years ago, but it generally over time begins to cool as a result. As we know, entropy results in the cooling of the Earth. And people wondered, how did organic material start? Well, there's two major theories. One of them is that organic materials started as a result of chemical reactions that were going on the Earth in the place of very specific molecules like methane and carbon dioxide and sulfur dioxide and ammonia, nitrogen-containing compounds. and that these organic molecules formed as a result of these chemical reactions going on as a result of massive amounts of electricity which were occurring on the Earth at that period of time. And this was shown by an experiment done by Miller and Urey, who showed that you can form amino acids with non-organic materials if you add enough heat in the form of electricity. So they added electricity to non-organic compounds and found that you could form organic compounds. On the other hand, another experiment showed that you can form nitrogenous bases as a result of specific heat and pressure inputs into non-organic molecules. So the second theory about how organic molecules came to appear on Earth were that the Earth has been early on, and still today, has been bombarded by massive amounts of meteors, and it's been shown that up to 19 amino acids have been isolated from the material on meteors. And this shows that some of that organic material could have likely come from the meteors. When they hit Earth, these amino acids existed on Earth and were able to somehow kind of form together chains and undergo some sort of replicatory event. So people still really aren't sure which theory, the began on Earth theory or the came from somewhere else theory, but these are two common theories that explain the existence of organic molecules on our Earth today. Now, the first life didn't occur until about 1 billion years after the Earth was formed, and it is thought that during this period that only kind of single-celled bacterial photosynthetic organisms existed in the oceans, and they were photosynthesizing, creating oxygen. These cyanobacteria that were creating oxygen in colonies called stromatolites, which left many, many, many fossil beds around the country, deposited oxygen into the atmosphere, which led to the formation of large amounts of iron precipitates, which you can see right here. These bands are iron precipitate, which resulted from the formation of solids when irons in the air, iron oxides, form with oxygen to form the precipitate. So, and you can find these all over the Earth, these precipitate solids that resulted from the oxygen revolution caused by the cyanobacteria about 3.8 million years ago. On the other hand, you had about almost 2 billion years went by before the first eukaryotic organisms existed. So that means that most of the organisms that inhabited the Earth up until 2 billion years ago were all prokaryotic, single-celled organisms. Most of them were photosynthetic, but by this time, many of them had changed over and adapted to kind of a more heterotrophic lifestyle. But one of the first single-celled eukaryotic organisms was called acritarch. About 2 billion years ago, had an acid-resistant cell wall. It looked like a dinoflagellate, which is a specific protist. These protists have organelle-like things. They're single-celled, and still all the organisms at this point are all marine organisms. Organisms didn't move onto land until much later. 1.5 billion years ago, multicellularity begins, and it appears to begin as a result of very loose associations of cells that form colonies. So multicellularity has been known to form colonies first, and then later on in evolutionary time, these cells actually became dependent upon one another and formed more aggregate structures where they're sharing nutrients and sharing structures and things like that, forming tissues, which are cells that come together to form have specific roles in the organism. So around 1.5 billion years ago, this multicellularity begins to evolve. If we look at the diversification of the eukaryotes, which is beginning to happen around 2 billion years ago, we see that the protista, which are the first eukaryotes, have some sort of ancestor, but they are rapidly diversifying. The opistheconchs, the Archaeplastida, the Rosaria, alveolates, Draminopiles, Disclaristids, the Amoebozoa, are all organisms that ended up giving rise to multicellular and single-celled plants. We've got the animals, fungi, all these organisms, the protists, ended up giving rise to the plants, the animals, and the fungi, which is important, and we're going to learn about that later. But the first major step in the formation of multicellular eukaryotic organisms was the diversification of these protist organisms that were both photosynthetic and fungi-like, saprophytic, which are organisms that eat dead organic matter, and heterotrophic, which are the ones that are going to lead on to the more animal-like organisms, which are these opistheconchs down here. So it's important to understand that this diversification that resulted from colonization of different habitats by the prokaryotic organisms resulted in a diversification of organisms that became even more diverse, which were the eukaryotes, which now have organelles and became colonial and multicellular. All right. As we said before, cells become colonial and multicellular around 1.2 to 700 billion years ago. These cells begin to live with one another and begin to form colonies that start to work together to form different types of tissues. This here is Volvox. It is basically a single-celled eukaryotic protist organism that is made of many parts, which at one point is believed to be many smaller cells that were photosynthetic on their own. Okay. So again, it's important to understand that after 1.5 billion years ago and moving into 1 million years ago, into the hundreds of million years ago, we have the eukaryotic organisms really starting to diversify and become interdependent upon one another. At this point, you have multicellularity, you have organisms that are both prokaryotic and eukaryotic beginning to adapt to a changing world. Something called the Cambrian explosion around 530 million years ago really ended up in the diversification of multicellular organisms, heterotrophic and photosynthetic and saprophytic that we know today. And today, basically, you see the result of the Cambrian explosion, which was a time period by which fungi, plants, and animals diversified on a rapid scale, not found in many other epochs of time. And here we have the trilobites, we have chordates. Chordates lead into organisms with spinal cords and backbones and dorsal hollow nerve cords. Sponges are an extremely efficient colonial multicellular eukaryotic organism that has very loose tissues, very simple tissues. Then you get onto organisms with an exoskeleton, or with hard skeletal structures, into more cephalization, which is kind of the head and tail region. So the Cambrian explosion resulted in organisms that ended up becoming the major plants, animals, and fungi of the world that we know today. This is just a basic illustration looking at the diversification of organisms, and also just showing Earth forms 4.6 billion years ago. Around 3.5 billion years ago, you have the first single-celled prokaryotic organisms beginning to occur down here, and then you have the Protozoic around 2.5 to 2 billion years ago. You have protist organisms beginning to form, and then the Cambrian explosion results in organisms that give rise to organisms that we know today.